Okay, we've we talked about how working out the pH of strong acids and also alkalis, but now we're going to turn our attention to weak acids. Okay, so GCSE, you said right, you've got a strong acid. It completely dissociates in water. 100% of it will dissociate. A-level is the same, really. But we bit more. We say right, 100% of it doesn't dissociate, really, does it? It forms H3O plus. And Cl minus. Now, a weak acid, you don't get 100% of it doing it. It's only a small proportion of the acid molecules which release the proton. So let's have a look at ethanoic acid, which is the sort of archetypal weak acid we're going to be looking at. Ethanoic acid. So, right. What's an equilibrium reaction? It's only a small proportion of the ethanoic acid molecules give their this acidic proton. That's the one, isn't it? To only a small proportion and give it to the water. So that is an equilibrium. Now, usually that would be the correct way of writing it, but it's usually fine. We don't usually bother with the H2O. We just take that as an understood, and we just put like H plus there. Okay. So this is a weak acid. All right. Let's have a look at what's going on here. Let's move this down a bit. Right. So if we wrote the equilibrium constant for this reaction, Kc, we would write it as K is equal to, I'll move it down a bit, K is equal to the concentration of the CH3COO minus multiplied by the concentration of the hydrogen ions divided by the concentration of the ethanoic acid. And more generally, what we'll tend to use, and we'll use all the time this convention, we'll call this weak acid, we call it HA. So this would be A minus, that's its conjugate base, yeah, and H plus. So we say for a weak acid, this equilibrium constant, and we give it a special subscript, we call it A for acid. Ka is equal to concentration of the conjugate base, A minus, times by the protons, divided by the concentration of the undissociated acid, HA. Now let's have a think about some values of this then. So if you look at Ka for ethanoic acid, so I'll write the acid down. Ethanoic, sorry. We'll just compare a few, yeah. So ethanoic, so CH3COOH. What is the value of Ka? Well, it's about usually quoted as 1.74 times 10 to the minus 5. Now, what's the units going to be? The units of Ka, well, you've always got like 2 lots of mole per decimeter cubed on the top and 1 on the bottom. So those two are going to cancel out. So the units are going to be mole per decimeter cubed. That's for, it doesn't matter which acid it is, because it's always about releasing 1 proton per molecule. So we've got ethanoic acid there. Let's have a look at another acid. Let's have a look at nitrous acid, not nitric, which is a strong acid. Nitrous acid, which is HNO2. So its conjugate base would be NO2 minus. And the value for that is 4.7 times 10 to the minus 4 mole per decimeter cubed. I'll put the units at the top there. Now, and then let's have a look at carbonic acid, which is H2CO3. Although its formula is H2CO3, we're only talking about it releasing 1 proton, so its conjugate base would be the hydrogen carbonate ion, and the value for that is 4.5 times 10 to the minus 7. So what does the size of Ka tell us about the acid then, how strong it is? Well, let's have a think about that. Well, if it's bigger, if you've got a big value of Ka, it means this on the top here, the A minus and the H plus is big and the HA is small. So basically then hopefully you can be able to see that the bigger the value of Ka is, the stronger the weak acid is. Okay, so bigger Ka, the stronger the weak acid is. So if you look at these, we've got ethanoic acid here, which is in vinegar. That's in the middle. Nitrous acid is got a smaller. It's got a bigger Ka value, hasn't it? It's only 10 to the minus 4 rather than 10 to the minus 5. So nitrous acid is stronger than ethanoic acid. And if we look at carbonic acid, well, you can see that's a lot weaker than ethanoic acid because that's like in the range of 10 to the power of minus 7. So that's a very weak acid. If we think, what would be the value for, you can't have Ka for a strong acid, but let's just see why. For a strong acid, well, if you've got a strong acid like HCl, and you've got H plus and Cl minus there, well, Ka for that would be H plus Cl minus over the concentration of HCl. And we just said there isn't any HCl, okay? And that would mean you'd be dividing by 0, which you can't do. In actual fact, you would always get a tiny bit of HCl, which is not dissociated. So this value will be very, very small, and that tends to make the value for Ka, like, it makes it huge, okay? So it's meaningless to talk about the Ka of a strong acid. It's really, I suppose, if it's a genuinely strong acid, it should be infinity, but it's only meaningful to talk about the Ka of a weak acid. Just before we finish this, and we're going to use these values in the next video to calculate the pHs of weak acids. Just before we finish this, let's just have a think about some things which you might not think has been a weak acid. Let's think about the ammonium ion, NH4. Now, so you could have this, for example, e.g. if you had a solution of ammonium chloride, you'd have ammonium ions. That has some tendency to give away a proton, and when it gives away a proton, it will form NH3 and H plus. So we normally think of the NH3 as being a weak base. We don't really think of NH4 being a strong acid, but of course that's exactly what it is. It's a strong acid, and it's got a Ka value. It's a very weak acid. NH4 plus is a very weak acid. The Ka for the NH4 is it's about 10 to the power of minus 10. So it's like a whole lot weaker than all the other ones. But it's just well to remember that yeah, whenever you have a weak base, it has a weak acid as its conjugate pair. And likewise with ethanoic acid, you think HA has got some tendency to give away protons. That means, and this is an equilibrium reaction, that means A has got some tendency, the ethanoate ion, some tendency to accept protons and go backwards. So this is actually, it is actually a weak base. So the conjugate acid, the conjugate base of a weak acid is always a weak base. And maybe we can just even expand that to the chloride ion. Well, the chloride ion is a potential base, isn't it? Because it can react with H plus. Well, what's the tendency of the chloride ion to react with H plus? It's virtually non-existent because HCl completely dissociates. So that means the chloride ion is a very, very, very poor base. Leave it there.